Welcome to our annual overview of the PDMP corn silage evaluation trials. My name is Hanna Wells. I am the liaison between Penn State and PDMP. I have taken over this role from Tammy Perkins. I guess if you weren't at the nutrition conference last year, Tammy had been with the program for 17 years and decided to step down. And so I'm kind of filling that role now. I'm very familiar with the project. I served as a research technologist for the evaluation project at Penn State. And so it was really an easy transition for me into this role. And so it's been a good experience. All right. So PDMP has a partnership with Penn State, and Penn State is kind of the one who carries out these research projects. And so Penn State has the grain hybrid trial, so it just kind of made sense to partner with them to do the silage trials as well. And in addition to this partnership, we have a collaboration with Cumberland Valley Analytical Services. So Cumberland Valley provides insights into analytical issues and trends in the industry. And then we have the advisory committee, which is producers, nutritionists, seed companies, and the folks at Penn State. So we all gather once a year and discuss the following year's protocols for the project. And lastly, we have the Northeast Consortium, which is University of Vermont, Cornell, and Western New York Crop Management. And the goal of this is to help work towards some consistency in our evaluation programs and interpretation. And this is our kind of core team. We're kind of lacking two main people right now at Penn State. We are trying to fill those roles, but Dr. Chris Canale and Dr. Alex Hristov have really stepped up and helped fill those roles. So to start out with, we have Chris Canale, who is the technology manager at Cargill Animal Nutrition. And we have Dr. Alex Hristov, who is a professor at Penn State in the Department of Animal Science. And then we have Jim Brining and Dayton Spackman, who are both research technologists at Penn State. And these two do most of the legwork. They get all the seed prepared, they plant, they harvest, they do all the data analysis. And lastly, there's me, the project liaison at PDMP. So here's a list of our host farms in 2020. This project is dependent upon our producer members who provide acreage for our testing plots. We cannot do this without their support. They do a tremendous job with the plots. So if you are one of them or know any of them, please extend your appreciation towards what they do. So this year we had 17 participating seed companies with 126 hybrids. So here's a list of all of our seed companies. I won't read them all off to you. We're also very grateful for their participation. We obviously wouldn't be able to do this project without them. All right, the overall goals of our program is obviously to test hybrids and improve characterization methods and broaden our collaborations. As I mentioned earlier, the Northeast Corn Silage Hybrid Evaluation Consortium, that's a mouthful, but again, that's with Cornell, University of Vermont, and Western New York Crop Management. And here are our evaluation program principles. So we do replicated environment evaluation. So we replicate hybrids 3 times across 3 locations in each maturity group. So we have 4 maturity groups. We have short season, mid-season, and then we plant mid-season hybrids in a late season area. And lastly, we have late season hybrids. And so within our results, we sort hybrids by dry matter within each test. And then we provide maturity subcategories at each location. So I will go over some of our data and I can point out those subcategories. And then we conduct our tests under typical crop conditions. So if a producer asks us, you know, what do I need to do to the plot, we ask them to do what they would do on the rest of their farm. So if they spread manure or they have a certain amount of nitrogen that they put down every year, we tell them to just manage everything as they would everything else. And then lastly, our goal is to report data to producers by November 1st. All right, so our Penn State season in review. So planning started on May 12th, which is, it's a little late for them to get started. But if you remember, we had a very cold, wet spring. And it took them about 2 weeks to finish up planting, and planting ended on May 28th. Harvest started on August 27th and ended on September 16th. So over a period of 3 weeks, they had everything harvested, which is, it's really good timing. I know when I was with the program, you know, we would oftentimes be at the end of September. So I think they did a really good job getting everything in the ground and harvested in a timely fashion. All right, so the growing season in review. So again, we started out with high rainfall and cool temperatures. I think many of us thought that we were going to have a repeat of 2018 and 2019. And I'm sure a lot of people planned for a very wet year, and Mother Nature threw us a curveball in most parts of the state. All locations had good fertility and herbicide programs. A few locations needed post-rescue treatments, but it didn't hinder any plant growth. So we had a very dry summer in most of the state. Southeastern PA escaped the drought and had our best yields. And we had many locations that were discarded due to drought stress. And so it was difficult to plan timely harvest with our rapid dry down, so that those harvest dates of September 16th, you know, I don't think we could have done much better than that. I think in some of our results, you might see some higher dry matters, but when you've got rapid dry down like we had, it was difficult. So we had 4 failed locations in 2020 in Juniata, Bedford, and Clinton counties. They were all discarded due to drought stress. And then we had to toss the trial at Bellefonte because of a herbicide application on non-Roundup Ready entries. All right, so I'm going to get out of this PowerPoint, and instead of boring you with a bunch of screenshots, I'll just show you where you can find our data. So the results are posted in 2 different locations, and I don't know if this makes it easier or more difficult, but Penn State posts the data as well as PDMP. So if you Google 2020 Penn State corn hybrid trials, this page should come up, and you will see there's contact information for seed companies, the cooperator locations, and then you can either click here to go down to the reports, or you can scroll down. And we have those 4 maturity ranges that I was talking about, the short, mid-season, and late season area, and late season hybrids. And we have Excel spreadsheets as well as PDFs for mobile-friendly viewing. And then if we go over here to PDMP, if you type in pdmp.org, it should bring you directly to the home page. And I just added this in here yesterday, so you didn't have to dig through tabs to find data. I just put a link right here that you can go directly to the data, or if you click up here in the research tab, it's going to be the first option down in testing results. And then we have the exact same setup as Penn State with how we have things laid out with the Excel spreadsheets and PDF versions. So each maturity group has 3 locations, and we have individual data for each one of those locations. And then we have combined data with all of those locations together. And so it's important that you look at all of the locations in addition to the combined data together, and not just base your evaluations and purchases off of one location that might be close to your farm. And so what I'll do is I'll bring up, I've got one of these individual locations and a combined location. We'll just go through what these spreadsheets look like. And so this is, my Zoom screen is hiding which location this is, but I think this was a late season. I think this was Landisville. So this is a Penn State README. We have to put this in there. Then we have a cover sheet. And then we have a background tab. So each location will have all this information with planting dates, herbicides, harvest dates. We include a field summary. And lastly, a weather summary that has precipitation for that field and the growing degree days. And then the next tab over is, this is the data tab. And things have kind of changed this year with our headers. We've added 3 extra columns this year, and Chris and Alex are going to go into what these 3 columns mean. But these 3 columns have to do with us running wet chemistry on NDFD 30 and starch. So we just kind of rearranged our tables a little bit, and hopefully they're a little bit more user-friendly and easier to read. But like I had said earlier, we sort all of our entries by dry matter. And then we have our maturity subcategories. So these are our medium late entries, which are 107 to 114 day. And if we scroll down here, we have a different group with our late season entries. And then going down, we have the statistics. So we have the mean, LSDs, and CVs listed down here at the bottom. And each one of these parameters up here that have a number are all identified down here below. And the next tab over is our trait key. So we're getting pretty full with our spreadsheet here. So instead of adding a huge trait name, we've designated it with a number. And so you can take that number, go over here to the trait key, match that number up over here on the left, and figure out what traits each hybrid has. And then lastly, we have the OMD story, which again, Chris and Alex are going to go into that in a little bit more detail, but this outlines how it's used and why we've decided to go this route. And so that's an individual location. And then we have our combined location data. This is a mid-season, these are mid-season hybrids in a late season area. And we don't have the background tab like we have on the individual sheets, but we have these are scatter plots. So we're showing the relationship between yield and starch, yield and NDFD 30, and yield and UNDF. And the way that these scatter plots can be used is, I always think of it like quadrants. So this quadrant is higher yield and lower starch. This would be high yield, high starch, low yield, high starch, and then low yield, low starch. And so you can look easily at each entry that's in these quadrants, and they all have numbers, and they can be, you can look up the numbers over here on the legend. We also have LSD lines in here, and any entries that fall within this LSD line are not significantly different from one another. So if we look at this line here, we can tell that entry 1 and entry 5 are technically not significant from each other. And so each scatter plot looks the same with the labeled quadrants. And they also have, we have the trait key and the OMD story in the combined data here as well. So that will bring me back to our PowerPoint, and I will leave you with this. We usually present our results at the nutrition conference every year. We have our annual advisory committee meeting on December 8th. So if you have any comments or feedback about our program, please let me know, and I can take it to our committee meeting and we can discuss it. So this is my contact information, my email and my phone number if anybody has anything to add. So with that, I'm going to turn this over to Chris and Alex if there are no questions. All right.
Alex, you hear me? Yeah, you wanna? I think what we'll do is Hanna, we'll have Alex run through a little bit of OMD, and then I'll jump back and kind of review some mean data and just source some relationships. So Alex, and I think you're going to advance this, Hanna, is that right?
I will advance the slides. Is this where you would like to start out?
Yep, you can. I think Alex can take the next one and we'll go from there.
Yeah, sure, Chris.
Yeah.
Thanks, Hanna. That was great. So you can move to the next slide. You know, my job here is to talk to you guys a little bit about the organic matter digestibility index and what is it about, how we came up with this. I've been on this committee or advisory committee for some years now, and what I kept hearing is that, you know, producers, nutritionists, producers particularly, they would like to look at, you know, one number that hopefully will represent the value of that hybrid versus the other one. We used to look, as you all know, at Milk 2006. We kind of discussed this for several years in a row and decided that this no longer represents actually accurately what the response in the cow is going to be. And that's why we thought quite a bit, and we came up with, I would say, a more simple calculation, but in my opinion, something that represents better the chemical composition and also digestibility of the silage. So basically, we include in this organic matter digestibility index all major nutrients, and as they are listed here, these are obviously starch, NDF, crude protein, fat. We also use lignin and we use ash for some of these calculations. Chris knows we went through several iterations on using NIR data versus wet chemistry. Of course, one is more expensive than the other. I will show you here maybe one slide with some of this data, particularly on NDF. But we decided at the end that for at least for at this stage, maybe if the databases improve and the prediction equations improve, we can go back to NIR. But at this stage, we decided that we'll use, for these calculations, we'll use wet chemistry. And what is involved here is NDF 30-hour digestibility, and this is wet chemistry. and then also starch, again by wet chemistry, because these are all in vitro analysis. One point I will make here, and I don't know if Chris, you are going to talk about this or not, but is on the starch digestibility procedure. You all know that I think this is wrong here. We are using 1 millimeter now and 4-hour incubation, but you know that the traditional starch analysis, starch digestibility analysis is 7-hour 4 millimeter. So we decided that variability can be decreased by grinding to a smaller particle size. And currently our procedure here is a 1 millimeter and 4-hour incubation. We also have a coefficient for crude protein digestibility. Total crude protein is analyzed, fat or fatty acids are analyzed, and we have a coefficient, fixed coefficient for these two. We use lignin as an indigestible part of NDF. I will talk very briefly here about UNDF versus lignin, but we decided to go with lignin. It's a more, I think it's more reliable chemical analysis versus something that will predict digestible NDF versus indigestible NDF for that part of NDF anyway. We also need dry matter yield, organic matter content of the silage, which is the ash analysis, to calculate organic matter, digestible organic matter yield. So I mentioned here milk 2006. So these components that we have in the index include 85% or more of the potentially digestible dry matter in corn silage. So very little is left out, and we think this represents pretty well what the potential digestibility of the silage is. So we have the formula here for both the index itself and digestible organic matter yield. Digestible organic matter yield is very simple. You are just taking the index and multiplying by organic matter yield, which is dry matter minus ash. This is, I want to just make a note here that this is heavily influenced by yield. That second part here, digestible organic matter, is heavily influenced by yield, more probably than the index, digestibility index itself. And it will be pretty variable from a year to year, just so you are aware of that. So Hanna, you want to move the next slide? This is just some of our background work that we have done, looking at ways how this index should be composed of and so on. What I'm showing here is when we looked at, that was a couple of years ago, when we look at NIR versus wet chemistry analysis for NDF and NDFD 30-hour. This is what we saw. Again, that's from the PDMP Penn State project. On the left side, you see the relationship for NDF, and on the right side for NDFD, NDF digestibility. Obviously, there is very good relationship in terms of NDF percent of dry matter, but when we get to the digestibility part, the relationship between wet chemistry and NIR is not that great. So this is the reason basically why we went to a wet chemistry analysis for NDF 30-hour digestibility. Hanna, move to the next one, please. Yeah, this is a slide that Chris put together showing again the discrepancy between the two analyses for NDF 30-hour, NDFD 30-hour. As you see, the two lines, one is wet chemistry, this kind of orange color, and then the blue one is NIR. And for the most part, they don't match over the samples that we have analyzed. Next one. Also, in terms of lignin versus UNDF, when we looked at these relationships, the relationship between UNDF and lignin is actually very strong, which of course makes sense. It's not ideal, but it is very strong. And when we thought about it, we decided that lignin, being just one simple single chemical analysis, may work better for our index than going into a complicated in vitro or NIR digestibility number. So that's one of the reasons we decided to use lignin for the indigestible part of NDF in the equation. Next one, Hanna. Whether we use lignin or UNDF seems like we are getting pretty much the same kind of data for the index. This is a relationship. I think it's for the 2018 or 2019 hybrids, and a very strong relationship between the digestibility index, whether it's calculated with lignin or whether it's calculated with UNDF. Next one, please. So Joe Warrens in Cornell is collaborating with us on this, and they plugged the OMDI into their CNCPS programs to look at relationships with milk yield. So this is what they found for one of the years. This is 2017 hybrids. Pretty good correlation in my mind. Pretty good relationship between the organic matter digestibility of the silage, the hybrids, and then the predicted milk production by the cows using the CNCPS. It may not be as great for different years, but for us this was a pretty good relationship. So next one, please. How do we recommend this is used? Here are some points. The OMD index is not an absolute value. So you are not going to say that if we have an OMD of 57%, digestibility of organic matter in this silage is going to be 57% in the cow. That's obviously not what we are saying. This is an indication of the potentially digestible organic matter in that silage. So understand that we are not predicting milk yield. There may be a good relationship with milk yield predicted by different models and so on. And that's not our intention. It's not milk 2006. We are not predicting milk yield per se. We are just saying that this hybrid may be more digestible than the other one based on this OMD index. Let's see. So we talked about this, and the final note here is that I think the important part when you are selecting a hybrid would be the index itself, but you have to look also at digestible organic matter yield. As I said, this is heavily influenced by yield. Yield will vary dramatically from one year to another, even on the same plot, the same location, and even the same hybrids. So just be aware of that. But you have to also look at this digestible organic matter yield, which is obviously based on the digestibility index. This may be the last one. Go to the next one, Hanna. Yeah, so this is just an example of 2019 hybrids for the different locations and the spread in the organic matter digestibility index. So as you see, there is quite a bit of variability there. If we take one of these locations, anywhere from 46, 47% to up to 57, 58%. Most of the hybrids will be in the range here for that location, Bainbridge, 46, 51, 52%, 46 samples were in that range. But we feel pretty good with the spread, with the range of digestibility for the samples that we have analyzed, which again tells us that there is an opportunity there to select based on this organic matter digestibility index. Chris, I'm pretty sure this is the last one. You want to take over?
Yeah, sure. And why don't you go ahead and We'll go through the next few. Okay, good. We're right at 2:30, so we've got another 30 minutes here. So just get everybody reoriented on what you'll see when you run to the websites and look at the data. Depending on where you're looking on maturity and so forth. Just a couple reminders that because of what Alex and I discovered with regard to the wet versus the NIR and so forth, the NDFD 30 and the IVSD will be wet chem, just to get everybody reoriented there, and then everything else is via NIR. But this is kind of the format you'll see when you look. Go ahead, Hannah. So in the next few slides, we're going to look at some relationships. Some of this data is simply the observation of where the hybrids fell, just to give you an idea of what what everything kind of looked like. And some of the slides will have some regression analysis, just to give you an idea of what might link up or what might not. So this is dry matter by maturity. We have maturity on the x-axis there. So we had everything from 85 to 100, 115, 16, 18-day hybrids, and then dry matter of the plants. And I think in general our plants were dry. We had several 35, a little bit under 35, but we had several that were above. And these are mean data, 3 reps. So it just gives you a snapshot of where the plant dry matters were. Next, Hannah, we'll just kind of go through these and let everybody take a look at them. This is basically NDF percent, ranges low 30s up to mostly caps out probably around 38 or 39. But I would say in general, many of these plants, most of these plants were low NDF plants. This contrasts with the New York and New England data. I'm going to show a little bit of that at the end here with regard to OMD, but when Joe shared the data with me, I think that there's probably 2 or 3 units more NDF than most of the plot data to our north in New York and New England. Our plants, again, were fairly low NDF. Just from a nutrition standpoint, we kind of need to be concerned about the NDF load going into cows, and then its relationship to things like UNDF and digestibility. So next, this is UNDF percent of dry matter across the observational data. Some low U plants, 9 or less, and then plants percent of dry matter, 10, 11, 12, 13, 14. These are likely higher U's than we've seen in previous years. We've been moving up in general, but these U's for probably 40% of these data were fairly high as a percent of dry matter. Above 12, 13, we had some approaching 14, some higher. So that's a chemistry that's relevant, and that's why we measure UNDF pretty much all the time. Next one, Hannah. So this would be U as a percent of NDF. Prior slide was as a percent of dry matter. This is a percent of NDF. Most plants were easily between 30 and 35, even closer to 40. That is likely higher than previous years. I think last year we had most of our plants between 25 and 30, maybe low 30s as a percent of NDFU. These plants are higher this year. And I think part of that, folks, is because we had lower NDF plants. So if the U fraction is fairly resistant, or if you will, I mean, we know environment affects it, but certainly it's going to comprise a bigger percentage of the NDF and low NDF plants. And that's what we had here. So next one, Hannah. So this is UNDF on a dry matter basis, expressed on the y-axis, and on the x-axis, it's simply plant dry matter. And I always like to do this because I I constantly, I'm sure you all do, too, get asked, hey, will whole plant dry matter affect you? And in our data, again, fairly controlled environments per se within the plots, but certainly we've got differences across the state. But pretty much year to year, if we just look at the dry matter percents on the x-axis of our data and we plot U as a percent of dry matter, we typically don't see any relationship there. So these plants, whether they're affected, if you will, by environment through other factors than dry matter, because our data just kind of shows this every year. Our square, there's virtually no relationship at all. Next one, Hannah. And this is NDFD 30. Remember, wet chem, NDFD 30. And this is expressed by UNDF on a dry basis. So x-axis is UNDF dry matter. Y-axis is NDFD 30. Relationship so-so, 0.3. Standard error 2.6. This is sort of what we see year to year when we express UNDF on a percent dry matter basis. Plenty of scatter there, plenty of error. So trying to, and we see this every year, folks. So whether it's circular statistic, meaning we are looking at relationships that naturally combine or don't combine. But in our data, we don't typically see this relationship. And the U's are NIR, and the NDFDs are wet chem. The folks at Cumberland Valley have shown Alex and I a lot of their data looking at NIRU versus wet chem U, and we signed off saying NIRU was okay, but we don't really see a relationship when we express UNDF on a dry matter basis. Next slide. When we move the NDFD with respect to UNDF as a percent of NDF, relationship gets a little better, 0.56. I can tell you that we look at this every year, and every year this relationship is somewhere around 0.6. Again, I don't know if I feel good about that or not, simply because I'd like this to be more robust, but perhaps not, because I have looked at other data sets, whether it's Cornell or Wisconsin and so forth, and when I do try to correlate NDFD 30, and many are doing it NIR, but when I can get a hold of wet chem data, and I will express UNDF as a percent of NDF, most of the time that regression is around 0.6. So it's happened to us every year. I saw it again in this year's data, and I think at this point, I'm pretty comfortable just telling folks, look, UNDF as a percent of NDF is going to account for about 60% of the variation in NDFD, about 60. I'm not expecting it to account for any more, quite frankly, and maybe no less. But there's, you can look at this two ways. You can say, well, good, it accounts for 60% of the variation. The other side is, well, there's still 40% unexplained in NDFD. Whether we got looked at what that other in this particular in our scope, we don't look at what's left, but I can tell you, folks, that number seems to be around 0.6 no matter where I look. Go ahead. And we Alex and I have done this too, and Alex mentioned this, that there's a few different ways to look at NDFD and to link it up, but a couple of years ago when Alex and I finished a lot of evaluatory work and looking, the lignin number is about right there, 0.7. So when Alex says it really, for us, the UNDF and then the lignin, we kind of got the same result, if you will. We ended up using lignin in the OMD. But those two data sets agree pretty closely. Okay, for corn silage, this is corn silage NDF, right? So don't extrapolate that to grass NDF, legume NDF, small grain NDF. But within corn silage NDF, fresh samples, we see lignin and U kind of hook up. Okay, next. Starch percents, pretty high. Most of them pretty high. Most of them above 35%, many above 40. A lot of high starch corn plants up in New York and New England too. And I looked when Joe shared me his data. But plenty of starch for the most part this year. Next. So this is IVSD, a 4-hour 1 mil. We've been doing this now 3 years. This is the measure we agreed to do in fresh corn silage. We very usual. We'll see numbers range from 50 to 65. We even have a few. We had one part that had really high in vitro starch Ds, higher for fresh corn silage than we've ever seen. But typically we'll see data 55 to 65% of starch, fresh corn silage using our procedure 4-hour 1 mil. I will add that we use this procedure on a variety of starch sources that ranges not only from corn silage, but to other starch sources, whether it's high moisture grains or dry corns and so forth. And I can tell you the analysis is fairly robust. I've seen data range in the low 40s for some pretty coarse dry material, all the way up to mid 70s and 80s for some wet, really processed high moisture material. So we vetted this, we think, pretty well, comparing it to NIR, comparing it to the C2. Alex and I had access to a few time points when we did this, when we chose this procedure, 2, 4, 8, 7, and we ended up with the 4-hour number. We felt the 1 mil control variability well. We thought the 4-hour was a pretty good estimate for 1 mil variability. So pretty typical data, 55, 65. We did have some higher ones. Next. This is a relationship of IVSD by plant dry matter. Again, x-axis, plant dry matter is 30, 35, 40, up to 50-ish, if you will. IVSDs on the y-axis, and basically no real relationship here. I get asked that question as well. Will plant dry matter affect IVSD? In our data, it does not. We can't see a relationship there. So, next. IVSD by maturity. So now we'll just look at maturity on the x-axis, 85 day, 90, 95, 100, and so forth, up to 118. That's on the x-axis. We have IVSD on the y. Again, not much, no relationship at all. And there's, and keep in mind, I didn't know if you saw the standard error on the previous slide. The standard error on this one's 5.5. So there's more error when we look at this data this way. Okay, when we try to plot IVSD across either a maturity or a plant dry matter. 5 units of standard error around these measurements. So it's gonna take, looking at this data this way across all of it, it's gonna take a pretty wide range of IVSD. Well, we can't find a relationship between maturity and IVSD. Next. OMD, so we'll jump over to this. Alex went through the equation, sort of the background, how we ended up where we did. We reported some of the plot data last year OMD. This year, everything got OMD because we all agreed to do WetChem IVSD and WetChem NDFT 30. Those were 2 key components to the OMD requirement. We met them, so now we have OMD on everything. So all of the tables you look at will have OMD. And Alex showed it's fairly robust. We can see samples 50s, low upper 40s in OMD, and yet we can have other samples that approach upper 50s and can even get across the 60% range. So keep in mind, folks, that this is fresh corn silage using in vitro starch digestibilities that are for fresh. Clearly, right, as you move corn silage in a silo after 100 days, 200 days, OMDs are going to go up because starch keys are going to go up. But these are fresh corn silage samples, and we detect differences all the way from upper 40s to upper 50s, low 60s. And as I'll show here in a little bit, a unit of OMD is at least in models, is going to be relevant. Next. There we go. So here's OMDs by maturity. Again, x-axis, 85-day to 118-day. OMDs on the Y. Couldn't get a relationship across maturity length, if you will, with OMDs. No relationship in the data set that we have for 2020. Next. OMD by NDFD 30, right? NDFD 30. I mean, we've assigned, Alex and I have assigned constant digestibility coefficients to protein and fatty acids. So those are kind of gonna, yes, we're gonna have slight variations in protein, slight variations in fatty acids, but certainly most of the prediction is going to come from NDF and starch. So this is the prediction when we include NDFD 30. And accounts for about 20% of the variation. I just wanted to, in our data, was interested in what might have the most weight around OMD. Again, remember, OMD is not one single time point estimate of one nutrient. It is not that. It is more of a dynamic, whole plant look at what might happen ruminally per se. But NDF accounted for about 20% the variation OMD. Next. IVSD accounted for about over 60% of it. So, right, I think we would all agree that starch digestibility, certainly in corn silage, is a big deal. It's a big deal to a dairy cow, and so is NDF digestibility. So, I'd say that between these two. You've got a pretty good contribution of fermentable nutrients to OMD, as it should. I mean, that's the equation. Yeah, could we include sugars and maybe residual NFCs, maybe some soluble pectins, glucans, and things like that, and maybe that's what Alex and I do next to account for the rest of it. But I'd say probably 80% of the variation or more is accounted by right now by fermentability of NDF and starch. Green corn silage. That's key because the IVSD is going to change as time in silo does. NDFD, some may actually, if enough solubles are removed, use might go up, and NDFDs might come down a touch. But starch by far is probably going to drive OMD as the plant kind of goes through fermentation. Next, got a few minutes left here. Okay, good. I think I've got a couple slides and then we can open it up. Wanted to make sure we have time for questions and discussion. So Alex, we've been working with the Cornell group probably 3 or 4 years now. And we've tried to get the table expression similar and so forth. We from an indexing standpoint, we've kind of gone the OMD route. The group up north with Allison, and Joe, and Tom, kind of still looking at what their corn plants might do in a model scenario around ME milk, and they also do intake. But I'm just going to show some ME milk relationship, and it's the version 7 prediction of ME milk. So Alex showed when we first started to at least get some data together, OMD and C and CPS, and showed, I think the relationship was around 0.7. At that time, and even still today, the Cornell group is offering wet chemistry NDFD and IVSD, but it's offered as an add-on, as an extra. In our data, of course, it's required. It's in. As we look at the CNCPS output this year, I took just a few of the samples that they actually had wet chem data on, and just quickly, again, it's only a few. Most of that data was NIR data. So when I just pulled out the 50 or so, I don't know how many, I don't know if I got them all, but and I just threw the wet chem OND versus the ME milk, accounted for about half the variation. So not quite as good with a fair amount of error. Very, very few observations, right? Not enough. I mean, not enough. But I was curious to see just directionally if what limited data we had for this year, how did it look? Now, I think Joe's gonna run some more analysis, assuming certain IVSDs, because they have the wet chem and the NIR and the FD, and that's probably what they're going to use. But you'll find this interesting. Next slide, because I did. So if I took all the data from OMD and all the data from that was used to predict the ME milk, and I don't have access to wet chem IVSD, but if I were to assign a 0.75 coefficient for IVSD and use all of that New York data, that's the relationship I get to the ME milk prediction in CNCPS version 7. So I only show you this because I think that the two groups have enough belief that while these are different indexes, they both are leaning to some type of biology in a dairy cow. So I ran this at 0.7, I ran it at 0.65, and I ran it at 0.6, and it all looked like that. So we're going to keep cooperating together, and we're going to keep an eye on both pieces of data, and we'll see if both groups can further refine their index. I thought that was kind of just to be like that. Okay, I think we're done, Hannah. We've got a few minutes for questions, comments. Colleen, I'm not sure how you want to handle those. If they ask them, or wrote some down.
Yeah, I think if folks would like to unmute themselves and ask a question, that'd be fine. And if you're more comfortable typing it in the chat, I will relay that.
Cool. And Hannah, when's the advisory meeting?
The advisory meeting is December 9th.
Okay. Yeah.
Let me double check that.
Yeah, that's okay.
I know I changed it. It was either the 8th or the 9th, and now I'm second guessing myself.
8th, is it? Okay. That's okay. Yeah, we'll take some notes if things come up, because we always try to use this presentation as a launch pad for what we talk about in that discussion. So, okay. Yeah, any comments or questions?
So question from the chat, are labs offering this? And I presume, Jim, that you mean the OMD index? Yep.
Yeah. Yeah, Jim, not yet. I think that Alex and I will look again. I think, Jim, we got this in a position where a lab can do it relatively routine. That was part of the criteria to kind of keep this thing moving, because if you remember, you were involved in some of the early OMD versions where we were including 12-hour, 30, and 240. We were trying to get the KDs, and yeah, Alex and I still have all those equations. But it made it more cumbersome for the lab. I think that Alex and I will talk, and see if it's time to approach a lab and offer it. I think, Jim, I would like to continue to sort of get more context around the biology of OND, whether it's through a model or an experiment that maybe Alex and I'll do. But I think we're getting close. I think we're getting close.
Yeah, if I can add to this, the index at this point is very simple.
Yeah.
We simplified it enough, and the analysis are a routine analysis. So I wouldn't see why, you know, a lab. You can calculate it yourself if you have the inputs, but the lab can do it too.